Hello everyone, welcome to the channel Learn Math with Shobita. Today I am discuss about groups, definition of groups, examples and some problems related to group theory. You can use this video to prepare kset examination 2025. So let us see what do you mean by group. A group, the definition, a non-empty set G together with binary operation star is called a group if the following conditions are satisfied. First option, closure axiom, that is for all AB belongs to G, A star B belongs to G. Associative law, A star B star C is equal to A star B star C for all ABC belongs to G. Existence of identity, there exists an element E belongs to G such that A star E is equal to A is equal to E star A. Existence of inverse, corresponding to every element A belongs to G, there exists A inverse belongs to G such that A star A inverse is equal to A star A is equal to identity. If all these four conditions are satisfied, then a non-empty set G with the binary operation star is called a group. Let us see some examples. Z set of all integers with respect to operation addition, set of all rational numbers with respect to operation addition, set of all real numbers with respect to the operation addition are all commutative groups where 0 is the identity element and minus A is the inverse of A in every case. So what do you mean by commutative group? Commutative group means the binary operation is commutative. That is, for all AB belongs to G, A star B equal to B star A, then we say that the binary operation is commutative. Now, what about the set of all natural numbers? Whether that is a group with respect to addition? No. See, the set of all natural numbers with respect to addition operation is not a group because the identity element 0 does not belong to the set of all natural numbers. What about set of all non-zero rational numbers? The set of all non-zero rational numbers, set of all non-zero real numbers, they are all groups, commutative groups with respect to multiplication operation. In that case, 1 is the identity element and 1 by A is the inverse of each element. Okay. Now set of all integers with respect to the operation multiplication is not a group, as for every integer 1 by A does not belongs to the set of integers, that is inverse does not exist. Therefore, the set of all integers with respect to multiplication operation is not a group. Further, set of m by n matrices with matrix addition as a binary operation is a commutative group. Here minus A is the inverse of A and 0 matrix acts as the identity element. Next example, GLNR means the set of all n by n matrices which are invertible. These matrices is a non-abelian group with respect to multiplication operation. A inverse is the inverse element and the matrix, unit matrix, identity matrix is the identity element of this group. Okay. So the set of all matrices, n cross n matrices, is a group if and only if it is invertible, that is determinant is non-zero. Next, I will solve one problem related to definition of group. Here is one of the most expected question in kset examination. If G is equal to the set of all matrices of the type matrix A, order is n by n, each entry is A and A not equal to 0, the subset of M and F, then option A, G with respect to addition operation is an abelian group, G with respect to multiplication is not a group, option C, G with respect to multiplication is a group but need not be abelian, option G, G with respect to multiplication is abelian. Let us check the options one by one. See, here all entries are A. So while seeing this, it seems its determinant is 0 because using row echelon form we can reduce it to a matrix with the single row, single non-zero row, and remaining rows are completely 0. So its determinant will be 0. So it seems it's not invertible, so it is not a group with respect to multiplication. Is it right? Let us see. Let us analyze the options one by one. So option is tells it is a abelian group with respect to addition operation. So if I take A and B, two elements of the set G such that A has all its entries A and the B has all its entries as minus A, then A plus B we get 0, but 0 does not belongs to G. So with respect to addition operation, this group this set is not a group because addition is not a binary operation here. Now let us analyze option B. Option B, C, D are related to multiplicative group. So let us check whether this set G with binary operation multiplication is group or not. So let E is an element matrix A whose elements are all A, and let B be the matrix whose all elements are B. Given this entry A and B are not 0. So I will define AB as this A into B. So I will get the matrix A as n by n matrix with each entry NAB, where A is not equal to 0, B is not equal to 0, n is not equal to 0. So NAB not equal to 0, hence clearly the product AB belongs to G. So closure property is satisfied. First property. Next, associative property. Further, matrix multiplication is associative, we know. So second property is also satisfied. Now let us check whether the identity element exists or not. We have to find an element E belongs to G such that A into E is equal to A. So if I take the identity element E as all the entries E as EEE, then after multiplication I will get NAE, NAE, n by n matrix, which is equal to A whose all entries are A. So equating I will get E as 1 by n. So here the identity element E will be of the form n by n matrix with each entry 1 by n. 1 by n, 1 by n, where n is the order of the matrix. So it is the identity element, it is not matrix, identity element for this set. Now further let us check whether the inverse element exists or not. So inverse means for any L belongs to G, we have to find a B belongs to G such that A into B, we should get the identity element E. So equating it, I will get the inverse inverse element, matrix element B as 1 by an square. It is a n by n matrix with each entry 1 by an square. Also this 1 by an square is not equal to 0. So clearly this B belongs to G. Hence this acts as the inverse element. Also further AB equal to BA clearly holds. Hence it is a commutative multiplicative group. Therefore the set G with respect to multiplication operation is an abelian group. Okay. This is one most important questions. So please share and subscribe the channel.